Okay, there we go. So we were on, let's see, 10, and this was another chart about basketball players and graduating, non-graduating, but that seems to be what comes up on Wiley a lot. And we were talking about unions, right? So in the last problem we did regarding basketball players and graduating, not graduating here, which was number 8, okay? Remember, we talked about the fact that because it's an and, it's a joint, we could put the big denominator, the total on the bottom, and then we could go inside and find the little specific piece of information where females graduated, and that's our numerator. And we had the answer. Okay, but this time we don't have an and. So, just to focus. Okay, so we don't have an and this time. Now we have a union. So I know that it says and here, but it says union in your sentence, which means or. Or you may end up seeing it like this: the probability that your student is female or did not graduate. And when you have that situation, you have addition and a subtraction. Okay, that's the deal. You have the probability of the first one plus the probability of the second one minus the probability of both. The big giant total, which in this case is 345, is the denominator for everything. Okay, so we're going to have a denominator of 345 for there, plus a fraction with the denominator for that one, minus a fraction with the 345 denominator for that one. Okay, now the probability that the student is female, all the way over here, that's 164 for my numerator. Okay, then my numerator for not graduating, you're going to go all the way down for that total, which is 86. That's my numerator. Now remember, we took into account this row and we took into account this column. And what happened is that this number, this 31, got counted twice. So that's why we're subtracting one of them out. We're going to subtract out females who did not graduate, which is the 31, because it was counted twice. And then we also talked about the fact you could put these in your calculator, right? Exactly the way that they are. Or you could just do the numerators. 164 plus 86 minus 31, get that total, then divide by 345. And when you do that, you should come out with 0.6348. And that will be your final answer. Okay, for the union. Does that sound good? Okay. All right, let's try one more then. So the next union they want us to try is the union of the events graduated and male. Okay, so it may look like this and it would say union, or it might say the probability that a student graduated or they are male. So it might look like that. And when you see that little OR in the middle there, that little or, that means you want the probability they graduated plus the probability they are male minus the probability they are both graduating and male. Okay, which leads us to, oh, pencil is kind of light. Okay, because it's an or, they're all going to have the same denominator all the way across. Okay, so the probability they're a graduate would be 259 as a numerator. Probability they're a male, that would be 181 as a numerator. And then because I went down this column and across this row, what got counted twice was the 126, because that is a graduated male. So that's what we're subtracting out. And I came up with 0.9101. Okay, so that's your union. So make sure that you can do the unions with the ors And you can do the joint with the, just go right in and find it over the grand total. Those are the two big takeaways from this chapter, okay? Sound good? All right, then we just have 3 more little piddly kind of problems thrown in there. All right, so number 11 says, this one's just like the bifocal one, where you have the employees and they have the single vision correction or the double vision correction. So you have 55 students in a class, 37 are taking it because it's required, they have to. The other 18 are using it as an elective, right? You get a list you can choose from and they just picked it off the list to take it as an elective. So 2 students are selected at random. Okay, we're going to do the 2 student draw. What's the probability that the first student is taking the class as an elective? Okay, so what would that probability? We'll stop right there. Okay, well, how many students are in the class total at this point? 55, right? And how many students are taking it as an elective? 18. So there's our first little probability. Okay, now we also want the probability that the second student is taking it as a requirement. So now remember, because you have drawn 2 people out of the same pool, you're not just dealing with one person. What's my new denominator? 54. You have to subtract 1. But my numerator wants to be the students taking it as a requirement, which just so happens to be 37. So that one wasn't affected. Okay. Now, if you multiply both of those together, I came up with 0.2242 as my probability. Okay. All right, this is kind of a silly question because they're trying to prove a point down here with C. Okay, so we'll keep going. So B again says we want a probability. We got 2 students. The first student is taking it as a requirement. Okay, well, my denominator is 55 at that point, and the requirement kids are 37. Now we want the second student. So remember, subtract 1 from your denominator. Second student is taking it as an elective. Okay, so my numerator is not being changed. Remember, with the bifocal and the single vision correction, we wanted to know the probability that the second one was chosen with the qualifications as the first. So this is also 18. What do we think this answer is going to be? It's going to be the same, exactly. Because, you know, multiplication, it's commutative. It doesn't matter what order you put it in. So what do you notice about these values? They are the same. I don't know why that one's in there, but it is. And that's what they want you to see. Okay. All right. Well, number 12, we're going to practice a union one more time. And number 13, I had to put on there because I kept getting emails about it. Not from here, but from another class. So that's why I threw him on there. Okay, number 12. So we're talking about airlines and flight delays and all that good stuff. Make sure that focuses. There we go. Okay, so we have airline A and airline B. We're comparing 2 airlines. So this is the number of times that airline has been less than 30 minutes late. That's pretty good. Here's 30 minutes to 1 hour late. This is over 1 hour delay, right? Then you're real angry over here. So we know we always want totals, and that's your job to fill in all those totals. So if I add up all the delays for airline A, we're looking at 925. And if I add up all the delays for airline B, we're looking at 775. That gives me a total of 1,700. And that sounds great because remember, right up here, it told us this gives data on 1,700 flight delays. So that means we're doing pretty good. Okay, if we just add up the delays, 835 were less than 30 minutes. 694 were between 30 and an hour. And 171 were greater than an hour. All right. Now we just have one question related to this, and it says, if one flight is selected at random, from these 1,700 flights, find the probability that the flight is more than 1 hour late or is occurring on airline A. Okay, that should be really clear to you then. You have a union. So you are going to be adding two numbers and subtracting another. Does that seem pretty clear when you read that? Okay, so first we're going to find the probability that your airline is more than 1 hour late. We're going to add that to the probability you are dealing with airline A. But then you're going to have to subtract out a flight that's more than an hour late and on airline A, because again, as we looked, because we're counting that number twice. Okay. All right. So we know our denominator for each of these three fractions is going to be the grand total. There we go. Okay. Then we're going to look for the total of more than 1 hour late. That's 171. So we just added up this column here. We want the total we're dealing with airline A. So now we're looking at this row. That's 925. And then if we actually circle them, like I tried to do here, but my pencil got wonky, you realize that 91 was counted twice because 91 is the delay of more than an hour and airline A. So that's what we're going to subtract out. And I got 0.5912. Ooh, don't fly airline A because there's like a 60% chance you're going to be more than an hour late. Okay. All right. So here we go. 13. Is everybody okay with this up here? Okay, or airlining. All right, here's the one that's just, it's just stupid and it's confusing and students just get weird on me. So I thought we would do it together. Okay, so 9.6% Americans traveled by car over Memorial Day weekend. 88.09% stayed home. What's the probability that a randomly selected American stayed home or traveled by car? Okay, so again, we have a union situation. We want the probability they stayed home plus the probability they traveled by car minus what? What is that third category? The probability they did what? Oh, hold on. That's your second question. You got it, Lydia, down there. So the third one will be minus both of these happen together. This would be that they stayed home and traveled by car. Well, does anyone else have a problem with that last one? Yeah, you can't stay home and travel by car unless you live in your car, I guess. Okay, so that means these guys are mutually exclusive, right? You can't be both. You can't stay home and travel by car. So what's the probability of this happening? 0. So we don't even have to worry about him. Okay, now we just have to worry about these. So that's not terrible, except that they gave us percentages. And so that's another little wonky thing that we haven't had to deal with before. So what you can do, you can leave the percentages. Okay, so, oh, whoops. So for the home, you could leave 88.09, but what is that out of? What would my denominator be? That's out of 100, right? So you could add these two together, realizing that because it's a percentage, it's out of 100, or you could change these to decimals and just add them together. You'll get the same thing, whatever you want to do. Just know that you should end up with 0.9769. Okay, now remember, and this is what Lydia was getting at, remember that when you have probabilities, they should add up to give you what? 1, and this doesn't. This adds up to give us 0.9769. So why doesn't it add up to be 1? Yeah, there's other options, right? You don't just have to stay home or get in the car and go somewhere. You can do other things. Maybe get on a bus. maybe you walk somewhere, maybe you, I don't know, whatever it is you do. But what it's going to be a drop down box, and the choice that you want is that some Americans may have traveled by other means. So that's going to be the choice you want in the box. And that'll do it for chapter 4. Okay. All right. Sound good? Ready to hit chapter 5? All right, I think we can do it. So chapter 5 is actually a pretty tiny little chapter. He's only the front and back of the first page, and then a single page. And then the rest of these are just examples. So it's really, what you're learning is not a lot, but we need to practice it a lot because it's just different. Statistics is just different. You come in with very little background knowledge, whereas, even if you come into college algebra, you knew algebra to begin with. So you had a nice foundation, but in here, that's not always the case. So chapter 5, we're going to talk about probability distribution. So this first part, all the way up to the part where it says formulas, you know all that. That's all review. So let's just see if we can remember this stuff. So we know about a random variable, right? This is just the variable whose outcome is determined by an experiment. You have to do an experiment to figure it out. We also know, remember, there's 2 types. That's from chapter 1. So we know that there's a discrete type and there's a continuous type, right? So that's review. You'll have that on the test, a couple questions on those. So remember, discrete, those are countable values. There are gaps in between. These are whole numbers. You have to count them on your fingers, right? So you skip from 1 to 2. There's a gap there. You skip from 2 to 3, right? There's a gap there. Those are discrete variables. Okay, so for example, anything that says the number of, right? If your little situation starts out that you want to find the number of, that's a discrete random variable, okay? Also, points, like in sports, like scores, okay? So that is something that's always done with discrete random variables. Okay, then we know the other choice would be continuous random variables. So those really involve, the key here is intervals. Anything in an interval, right? So a decimal, a fraction, the in-betweens, okay? And that's just, it's an endless amount of stuff. But if you see amount, because that's going to indicate money. And we know money has 2 decimal places in it, right? So amount, it could be a length. It could be any amount of time, a weight, a price. I mean, just et cetera, et cetera. I mean, it's just really endless what could be continuous. And then we already talked about probability distributions. We said, oh no, we didn't actually. Okay, I'm confused with frequency. So remember, we used frequency distributions where we had our little charts, where we would, I don't think I have one anywhere, but remember, they're the little charts. They have all the, your variable listed. Sometimes they have classes over here, and then they have frequency. They have relative frequency, the percentages, all those things that you found for chapters 1, 2, and 3. Those are frequency distributions. Well, now we're going to talk about probability distributions. So we're going to take it a step further. So these are tables, not really graphs, but tables that list or show all the possible values that your random variable can assume and their corresponding probabilities. So we no longer have all that extra information. We simply have the numbers that your random variable can be, whether they're whole numbers for discrete or intervals for continuous, and then next to them, all their probabilities. And remember, we also kind of talked about the fact that probabilities are just relative frequencies, right? Because they all have to add up to 1. Okay, so the probability of a variable X must lie, equal or lie between what two numbers? Remember that? 0 and 1. Remember, all your probabilities have to be between 0 and 1, and we know they all have to add up to equal 1 in the end. So that's really important. This is also extremely important. Probabilities, they're approximate. Statistics is not an exact science. It's just not. It's not an exact math and it's not an exact science. So what you are finding, they're approximations. I mean, we don't even use fractions, right? We only use decimals. And then what do we do with the last decimal place? We round it. So we are definitely approximations. Anything in statistics is an approximation, okay? All right, so for your frequency distribution charts, remember we had all these lovely little formulas. Remember that? With our frequency distribution chart, depending on if it was ungrouped or grouped, we would find the mean, we would find the variance and the standard deviation. Now we didn't memorize any of that stuff because we just did it in our calculator. But we had all these formulas for frequency distribution charts. Well, we're not going to have frequency distribution charts anymore. We're going to have probability distributions. So we're going to need some different formulas because we don't have numbers to plug into those equations any longer. That's what you see here. This is a probability distribution chart. Here's your variable. This is for a discrete variable because look, it's 0, 1, 2, 3. There's no intervals. These are the probabilities associated with each one of these random variable values. Okay, so if you were given this information in a probability distribution, could you find the mean, the variance, and the standard deviation? Well, yeah, but you don't have formulas yet, right? Because you can't use the ones we learned. We no longer have that info. So we got to put in some new things here. So first of all, most of the time, they're not going to call it the mean anymore. They're going to call it the expected value. So if you hear that, that still means the mean. So you may see mu, remember that's the mean, or you may see E of X. Remember f of X from algebra for a function? E of X would be the expected value. And so the formula for that is the summation of X times P of X. Okay. Then this is very rarely asked for anymore. Variance is kind of like done. But if they want variance, it's little baby sigma squared. Okay. And it's going to be the sum of X squared P of X minus your mean squared. And then, of course, we know standard deviation is just the square root of the variance. Okay, so this is the variance of a discrete value. This is the standard deviation of a discrete value. This is the mean of a discrete value. Chapter 5 is only dealing with discrete random variables. That's it. And then after test 2, we're going to spend the rest of the class talking only about continuous random variables because discrete variables take up such a small portion of statistics. A lot of things that we measure and test and look at are over intervals. So, okay, there we go. Well, the good news is you don't actually have to know these. Yeah, they're on your key formula chart, but guess what? Calculator handles it. It knows. It can distinguish based on the numbers you put in your lists. It will know whether it's a frequency distribution or a probability distribution for a discrete variable. Your calculator just knows, and it will handle all this for you. Notice we're talking about mu, we're talking about sigma. Those are all population variables, right? Population parameters. We're no longer talking about samples anymore either. So no more samples in for this chapter. Okay, so let's see. Let's go through and do this by hand and see what we come up with for this little chart. And then we'll throw it in our calculator and just make sure that we can still remember how to do all that stuff. So here we go. Here's all the information you need. These are the values for your discrete variable, 1, 0, 1, 2, 3. These are your probabilities that match up with it. But if we're going to use the old school formulas, we're going to have to make 3 more columns. So first column, x times p of x. So we're going to have to multiply these guys together. So if I do that, I get 0, 0.2, 0.7, and 0.9. Okay. Now, by the way, I could add all these probabilities up, and sure enough, they equal 1. And I could add up x of p of x, and I get 1.8. Okay. We're going to need that summation for our formulas. All right, my next column is x squared. So I'm going to go over here. I'm going to square 0, square 1, square 2, square 3. And then the last column I'm going to need is x squared times p of x. So if I multiply these two numbers together, I get 0, 0.20, 1.4, and 2.7. And if I sum up that, I get 4.3. Okay. Now let's see how all that gets put into our little formula area. All right, well, first of all, this is the mean, right? Or the expected value, just depending on whatever they label it as. If you look at our formula, our mean is the sum of x p of x. Well, that's this column. So this sum that we found, that's our mean. Okay. All right, here's our variance. Okay, so remember our variance looks like this. It's the sum of x squared p of x. Well, look at there. This is going to be 4.3 minus the mean squared. And our mean was 1.8. So to find your variance, you're going to need this column's total minus the mean squared. And I came up with, I think, 1.06 for that. And then here's our standard deviation, which is just going to be the square root of the variance. Decimals are weird with square roots. The square root of 1.06 is 1.03. That just doesn't even seem right, but it is. Okay, so there you go. That's how you would do it by hand if you just were really bored and hated yourself, right? Okay, so let's look at how to put it in our calculator. All right, so remember, you're going to need 2 lists because you have 2 pieces of information. Okay, so you are going to have your x's in L1, and go ahead and label it so you don't forget. And you're going to have your probabilities in L2. Okay, so if you have the old school calculators, like a few of us in here, once you get to 1 var stats, you're just going to put in, okay, L1, L2. If you have the newer version, it's going to want the list, and it's going to want the frequency list. Now it's going to, when it starts to make more sense. Your list is L1, your frequency list is L2, okay? That's like your relative frequency over there. And that's what you're going to end up with. All right, so Yolanda, if you're watching this, honey, you're not going to be able to see what we're doing, but we're just putting stuff in a list. Okay, let's turn this on. Remember, list is stat, edit. And then we're going to go 0, 1, 2, 3. And then we're going to do 0.15, 0.20, 0.70, and 0.9. Okay, so we're going to quit. We're going to go stat, calc, remember, 1 var stats. All right, Now, when it asks for list, you're going to put L1. When it asks for frequency list, you're going to put L2. It comes out really beautifully from here on out in the class. You don't have to get weird like we did in the other chapters. But for this one, if you have the old kind, you're just going to put them in order, just like this. And there we go. Okay. That one did not come out right. What did I do wrong? I must not have put something in. Oh, I did. I did do that. Thank you. I mean, I slightly want to come strangle you for letting me do weird stuff, Kayla, but that's okay. You came out in the end. Okay, yeah, I started mixing them. How about that? Okay, thank you so much, dear. Okay, let's try this again. Stat, calc, 1-bar stat. Yay, okay, there we go. All right, so this is what you should have come up with. So let's look and see. Here's our mean right here, 1.8, done, okay? Now remember, you don't have the variance on here, but you should have the standard deviation. Remember how I told you the calculator just knows? It doesn't even give you a choice anymore because you're always going to be sigma with a discrete random distribution. So here's your standard deviation, 1.03, right here. And then remember, you're going to take this value and square it to get the variance. Now, it's always nice to go out a few decimal places. And if yours is newer and doesn't let you do all this while your screen is there, you'll want to write that down, that number down. But then when I square it, there's my variance, and it's 1.06. Okay. Does that sound okay with everyone? So it just kind of gets even a little easier here and helps you out. Everything should be in order the way it should be. Okay. Sound good? All right. Okay, so we can turn the page here. And then I'm going to kind of see what you, that's not right. There we go. Okay, so this is a survey. It asks families how many vehicles do they own. The results are shown below. So they asked how many vehicles. That would be the number of vehicles. So it's a discrete random variable, right? You can't have 2.3 cars or whatever. So from 0 all the way to 6, all right? Results are shown below. They've already figured up your probabilities. Now, we could, just for fun, if you guys really want to, fill in the rest of this chart and use all those big formulas like we did, but we already did one of those. Are you guys okay if we don't fill that in and we just put it in our calculator? I will tell you mine is filled in and it is on Blackboard under content. So if you want to see those later and go through it just for fun, it is there. Knock yourself out. Otherwise, you really don't need this because it never comes up again, right? We're going to put these in L1 and we're going to put these in L2. And then we're going to go for it. Now, I already hear some clicking, so we'll go ahead and do that. These questions would be questions we need to answer without the calculator. This would be our 1-bar stats stuff we need. So since I already hear clicking, let's go ahead and click, okay? And then we'll come back and do the other stuff. You guys are ahead of the game. Love it. Okay, let's see. Stat edit. I got to clear these out. Okay. Okay. Also, I want you to really notice something, which sounds stupid right now, but it's going to be a big deal later. Did you notice on the page before and on this page with these discrete probability distributions, what number does X always start with for these two? Anybody notice that? 0. That's super important. That is a characteristic of a discrete random variable probability distribution. We're going to get to that in a minute, and that's going to be really important. 4, 5, 6. Okay, let's see. I'm going to be super careful here, not throw in weird numbers. Okay. All right, so remember, always a good idea to label. So we labeled L1, L2. Okay, now we're gonna do our stat calc 1-bar stats. L1 and then an L2. These are the numbers you should have come up with. Okay, make sure that looks good to you. So our mean or our mu or expected value is 1.52, right up here. That's that. Now notice it also seems to be this column every single time. But remember, what were the formulas for the discrete random variable? It's the sum of the first column of the xp of x. So that's why these are the same every single time, because that's the definition of the mean for us for this chapter. Okay, and then remember there's no s of x, so we don't have to worry about that. But here's our standard deviation, 1.45. Okay, and then if I go out 4 decimal places or so with him and I square him, that's going to give me my variance, which would be 2.11. Okay, is everybody okay with those numbers? Is that what you got? Okay, good deal. All right, so let's go back up then and answer some probability questions. Okay, so what is the probability that x is greater than 5? Well, here's our x's, here's our probabilities. This says greater than 5, which means what number in our case? 6. There's the probability it's greater than 5, 0.02. That's it. Okay. All right, let's think about this one. What's the probability x is less than 4? Okay, well, how many x's are less than 4? There's 4 of them that are less than 4, right? 3, 2, 1, and 0. So I need to add their probabilities. So I'm going to add up 0.10 plus 0.25 plus 0.25 plus 0.30. I came up with 0.90. Okay, let me also show you something. And again, this is going to come in super handy in either the quiz or the homework. Remember that all the probabilities add up to be what? 1. Well, it's not too bad in this case because we only have a total of 7 lines, right? Well, if we had a huge number of lines, which you're going to have one that's kind of a pain in the butt like that, and we wanted to be, and this said, what's the probability that something's less than 4? Okay, well, we could add up everybody whose probability is less than 4, or if it was easier, I could add up the opposite. And I could add up 4 and bigger, which would come up to be 0.1. And then I could do 1 minus that. And I would get the same thing. So I could also take these, which are not included, add these 3 together. You get 0.10. And do 1 minus 0.10. And you get 0.9. Does that kind of make sense a little bit, or is that weird? We'll come back. It's okay. Just marinate on that a little bit. Okay. All right. What's the probability x equals 1? Well, that's 0.25, right? If x is 1, probability is 0.25. Everybody okay with that one? All right. Let's try 3 more. Now let's do these bother some students. So remember, think of it like money. You guys are really on top of your money. Okay. So what's the probability that a family owns more than 3 cars? Well, that's easy. More than 3 means 4, 5, or 6, right? Okay, so I'm going to add together 0.05 plus 0.03 plus 0.02, and I get 0.1. Easy enough. Okay, this is the one that bothers some students. What is the probability a family owns at most 2 cars? At most 2 cars. Okay, so if you're confused about what that means, change it to dollars. So if I say I need to borrow some money, at most $2, just at most $2, would you give me $3? No, you'd give me 2, maybe you just give me 1, because I only need at the most 2. So it could be 2 or less. Does that make sense? 2 or less is what we're looking at. So if I'm 2 or less, my probabilities are 0.25 plus 0.25 plus 0.30. And that is going to give me 0.8. Okay. And then what's the probability that a family owns less than 6 cars? Okay, this is the one I kind of wanted to talk to you about. I hinted about it before. Okay, so owns less than 6 cars. So you could add up all of these right here, right? That's less than 6 cars. Add them all up, you're going to get 0.98. You're done. Or if you had a really long list, what if you had something with like 15 numbers? You could subtract from 1. So instead of saying less than 6, I could have taken the one that I'm not using, the 0.02, and done 1 minus that and gotten the same thing. And I didn't have to add all of those together. So there will be a question on Wiley, and I'm going to show it to you on Thursday, where you do have, it's not huge, but it's just inconvenient. It's quite long. And you can either add them all up, or you can do 1 minus what's not wanted, and you get the same answer. So it's just kind of another way to think of it that will save you some time. Okay. Okay, sound good? So those are in general discrete distributions, just in general. Okay. So we're going to put continuous on hold till chapter 6. That'll be sometime in March after the test, right? Okay. Well, we're going to narrow it down even further. Now we're not just going to talk about discrete variables in general, which would be whole numbers. We're going to talk about specific discrete variables. So there are specific discrete distributions that we can use to help us and save us time in statistics. So a few examples of those are binomial. That's what we're going to learn in this class. This is a table of binomial probability distributions. That's what we're going to do. Okay, there's also Poisson. That's really out of our elementary statistics range. And then there's hypogeometric, same thing. You can take entire classes. You can have Poisson 1, you can have Poisson 2, you can have entire courses on just these distributions. I mean, you can fall down the statistics rabbit hole and never be seen again. But this just is going to give you a little bit of a lot of different things. So this is the one we focus on for discrete. When we go to continuous, we're going to focus on the normal distribution. Okay. All right. So how do you know if you're going to use a binomial distribution? Well, one of the reasons, let me step back for a minute. Why would you use a binomial when you have all these formulas here? Well, even though this was really nice, somebody gave you these, right? The textbook found these probabilities for you. If you were doing a study and you were trying to put together a project, you would not only need your variables, right? How many you have, you would need the probability that every one of those occurrences is going to happen. And that can take years to develop and work through with a lot of manpower. But if you can take your experiment and set it up in such a way that it meets certain criteria, like a binomial distribution, we're going to talk about those criteria, then they've already, statisticians for years and years and years have already found the probabilities. So if the parameters of your study match my study, I can tell you those probabilities. You don't have to find those on your own. You just focus on your particular study, and these numbers are going to match whatever it is you need. So by using a distribution that's already been made, it saves you so much time. So when you're formulating how to put together a study or a paper or something like that, you use parameters already in place so that then you can piggyback off other studies. The wheel has already been invented, right? Don't try to invent another wheel. Take what's been, they always call it standing on the shoulders of giants. Have you heard that expression before? People have already done research. You take what they've done and take that as your starting place and do something else. Don't start from nothing, don't start from scratch. So these probabilities have already been developed. So if you're coming up with a study and you want to use, and you have a discrete variable, and you want to use a binomial distribution, here are your requirements. First of all, you have to have n identical trials. All right, that's what n is going to be defined as. Maybe it's 4, maybe it's 100, but you have to have a certain number of identical trials. You're going to do the same experiment this many times, okay? You can only have 2 outcomes per trial. Okay, now we're really narrowing it down. I can no longer throw a die, right? Because that would be 6 possible outcomes. Can you think of a real common one that would only have 2 possible outcomes? Flipping a coin. That is the quintessential binomial distribution. 2 outcomes. Okay, heads or tails? All right, your probabilities of the 2 outcomes, hold on, I spelled that really weird. Probabilities of the 2 outcomes remain constant. They don't change. Okay, your probabilities remain constant. And then last but not least, your trials are independent. Okay, doesn't matter how many times you did it before, your next trial is still independent of the others. Okay, so those are your 4 requirements for it to be considered a binomial distribution. And then you get to use all this data, and all you do have to do is do your experiment. Okay, all right. So let's kind of go through and let me tell you a few things real quick. So first of all, as you can guess from number 1, the number of trials that you do that are identical is going to be n. That's what n means. Okay. The probability, I'm going to say of success, but is p. Or it could be the outcome you want. Whatever you consider to be what you want, what you're testing, that would be p. Okay. And then this sounds dumb, but the x value is x. So that just means you have to decide how many, within your n, how many x's are you going to have? And that'll make sense when we look at this a little bit more. Okay, so given these 3 variables here, oh, let me give you one more. Okay, the probability of failure, they can't use F because that's frequency, so they use Q. Okay, so that would be the opposite of what you want. All right, and then you get these really nice, easy little formulas. Now, these are not in your calculator. You are going to have to remember these, but they're on your formula sheet, okay? So for a binomial distribution, your expected value or your mean is simply n times p. We can totally do that. It's not some crazy thing, okay? Your variance is going to be n times p times q. And then your standard deviation is just the square root of that. Now, the great thing about this is that even though you can't put this in your calculator, when I say that, I mean it's not programmed in. Please put it in and multiply it and take the square root. This is very easy to find. This is very easy to define. This is the very first time you've ever been introduced to a formula where you don't have to find the variance first, right? We don't have some crazy complicated formula. We can just leave the variance out because frankly, I don't know that they ever asked for it again after that point, okay? But if you want to know where they are in your key formula sheet, just so you have an idea, here's chapter 4. Oh no, we're on 5. So we're 5 on the back. Okay, here we go. Binomial distribution, they don't even give you the variance because you don't use it, but mu is n times p. Standard deviation is square root of n times p times q. You don't need hypergeometric. You don't need Poisson. So you can get rid of that. Okay. Well, let's jump right in then. Okay, this is our last page of new material. This is just going to talk about binomial probabilities. All right, well, if you don't use your chart and you don't have a calculator, this is the formula for coming up with every probability in a binomial distribution chart. Notice we have one of those combinations. We have all kinds of weird stuff happening. I don't think I've ever used this formula, even back in the Stone Ages, but they want you to just see this is how you would come up with the probabilities. Okay, we talked about n is the number of trials. We talked about p is the probability of success. We said q is the probability of failure, but look at this little formula. This is super duper important from here on out the rest of the class. They're never going to give you q. They're going to give you p, and you have to know q, but they will never give it to you. So q is 1 minus p. Because think about it. P is the probability of success. All your probabilities add up to be 1. There's only 2 outcomes. So how are you going to find the probability of failure? Subtract them. Okay. All right. X is the number of successes and n trials. You don't have to know this one down here. Okay. So we are going to get ready and jump right in here in just a second. But first, let's look at your chart. So here we go. This, okay, is going to give you all the probabilities that you need. Notice here's your n, okay? So if you have a trial with 1 n, if you have 2 trials, 3 trials, 4 trials, all the way, I think this doesn't go too crazy. This goes to 20 trials, okay? Now let's look at your x's. Remember how before I pointed out that on all your discrete distributions, your x value started with 0? So your x values go between 0 and n. So if you're only doing 1 trial, you only have x's 0 and 1. If you're doing 6 trials, you have x values 0 to 6. You have 7 trials, you're 0 to 7, okay? So these are your discrete random variables for 7 trials. Bless you. All right. And then this is your percent of success. This could be 5%, 10%, 20%, 30%, 40%, all the way up to 95%. These are the probabilities that you're finding down in here. Okay, these would be the answers to the questions, what you see here. Okay, so let's see what we can come up with. And then we're going to also find out that in your calculator, there's a distribution button. And it has every known distribution in statistics from here to doctorate level statistics classes built into your calculator. So do you really need this? No, but you have to know how to read it. And you know, I love a good calculator. Binomial distributions are easier to read on a chart than they are the calculator, believe it or not. It's just faster, okay? But I want to show you how to do both. Okay, so here we go. 5% of Americans eligible to donate blood actually do. Okay, this is important. They gave you a percent here, 5%. All right, so this, I'm not even on the right page. So this that they gave you is going to translate into your P. But I can't put 5%. You guys know that. You don't use percent in anything. So how do I translate 5% to a decimal? 0.05. You want to divide by 100. Okay. All right. You randomly select 4 eligible blood donors. Well, that's kind of like 4 trials. That's your N. Okay. That's how many people you're testing there. And you're going to ask if they donate blood. Okay, now we also need Q because we're going to find the mean and the standard deviation. And remember, they don't ever give you Q. How do you find Q again? Good. So I'm going to do 1 minus P. That is my Q. So 0.95. Perfect. Okay, Now I want to create a binomial probability distribution chart using this data. Okay, here we go. N is 4. That's the first thing I do. Here's 4. Here's N is 4. So this is what I'm looking at, is this little section here where N is 4. Everybody agree with that? Okay. Now my P is 0.05. I go up to the top. So actually, I don't even want that giant rectangle. What do I want? These 5 little numbers right here. That's where I get my information. So if I scoot this over here, okay, when X is 0, which means 0 people, 0 out of the 4 said they donate blood. That's a probability of 0.8145. One of the 4 say they donate blood, 0.1715. 2 of the 4, 0.0135. 3 of the 4, my gosh, we're getting so tiny. And then what are the chances that all 4 of those randomly selected people all donate blood? 0. It's just not going to happen. And then if I add all these up, just to be safe, what should all that add up to be? 1, or at least close to it. I don't know what it adds up to be, but it'll be pretty darn close. You made a binomial distribution chart, and that's all there is to it. Okay, so you found all of that right off here. Does that make sense? So here's your N. Here's your probability of success. So that's going to be a decimal, right? In this case, it was 5%, 0.05. And then you just match up the numbers with your variables. Okay, let's finish this part down here, and then we'll do this one, and then we'll compare it on the calculator. Okay, so the mean, if you go back, remember, to find our mean, that's just N times P. So that's 4 times 0.05. Our mean's 0.2. All right, well, this does actually want the variance. That's sigma squared. Make sure you know what these variables mean, by the way, because it's only going to get tougher. Okay, my variance, remember, is N times P times Q. So it's going to be 4 times 0.05 times 0.95. That's 0.19. And then my standard deviation is just going to be the square root of that. So that's going to be the square root of 0.19, which weirdly enough is 0.44. And there you go. Okay, I guess I could go ahead and show you a calculator, and then we'll do example 3 next time. Okay, so notice how nice and easy, and it was right in front of you, and it was like just right there, right? Okay, let's talk about how would you find that on your calculator. Okay, here we go. So we no longer need lists, believe it or not. That's all been programmed in here. But see this button that says vars for variables? Okay, right above it, you see DISTR. That's distributions. So you're going to have to hit your second button to access it. These are every distribution known to statistics. So I see a lot of normals and inverse norms. We're going to get to that in later on. T-charts. This weird little thing, that's chi-squared. That's a distribution. The whole class is on chi-squared. Okay, we have F charts. Oh, we got a couple of binomes. We're going to use one of those. One of those is our binomial. But if you keep going, you got a couple of Poissons. And, hold on, sorry. Here are your hypergeometrics, which we don't have to worry about. But you want one of these two. Now, we have to be careful. You have to pick the right one. You want binomial PDF. If you pick CDF, that's going to do this weird binomial one for a continuous random variable. We are not continuous, right? We're discrete. So we want binom PDF. Everybody got it? Okay. All right. So if you have the old school ones like some of us do, that is certainly not very helpful. Okay. If you have the newer ones, then what you're looking at is, let's see, you should see trials like this, P, X value. Is that what you're looking at on the newer ones? Okay. Oh, you can't even see it. Sorry. Okay. So if you have the newer ones, you're looking at this. Is that correct? Okay. So what you're going to put in, remember your trials, that's in. Your P is your P, and your X value is going to change. It's going to be your X. Now, here's the thing. When you won't have all your values presented to you in a beautiful chart, it's not like one bar stats where it just gives you everything. It's going to give you one answer at a time. So, for example, if I want X equals 0, if I want this 0.8145, I'm going to put in 4 for my trial, 0.05 for my P, and then I'm going to put in 0 for my X and hit enter. Okay, if you have the old school ones like me, okay, then what we're doing is same order as they are. We're going to do our N, comma, our P, comma, our X value, and our first X value is 0, and we hit enter. And sure enough, 0.8145. Now, the calculator gives you every possible decimal. So that's the answer for X equals 0. See where I'm going with this? Now I got to do it for what? X equals 1. So now I have to go back in. Now, you know, guys, you have that function where I can't do it on mine because this is like a simulated one. But, you know, you can, let me borrow, what do y'all mind if I borrow yours? Can I borrow yours, Lydia? I'm sorry, honey, I won't breathe on it, I promise. Okay, thank you. Okay, so all right, let's see if I can get, hers is the fancier one. I might have to borrow the old one. Oh, it's 12:15. Okay, I'll start packing up, but I just wanted you to, okay, so if I go down here to binomial PDF and I do 4 trials, 0.05, and then I go to 1, okay, there's my next one. You know, I can always go up here. Remember this function? If you go up and you highlight it, all I did was hop up and then I hit enter. And then I can go over here and just change the X value. Does that make sense? And then I can go up, click it, and just change the next X value. And I can keep doing that and keep doing that, and it will save you, thank you, dear, a little bit of time. But we'll talk about that more on Thursday. But really for binomial, if you can, I think the chart is where it's at, personally. Okay,